for each of these types of resources that are present in all of these parks in some combination, right? Every park has some bedrock, every park has some soil and water and vegetation and wildlife and human infrastructure and so on and so forth. Each of these types of resources is explained on our course website, and I'll release here in the next couple of days the specific submodules under bedrock and soil for first walking you through what is meant by this resource. There's a lot under the heading of, for example, vegetation. And in a forestry program, obviously our first thought is going to be to the trees, but as it turns out, specifically in terms of recreation management and the habitat management that kind of goes hand in hand with that, we have to pay sometimes more attention to all of the other vegetation, because as we'll see in that unit, the trees, if they are mature trees in healthy functional soil structures and with reasonably moderate hydrological regimes, mature trees don't really care that much about forest and outdoor recreation, except for specific species. So coastal redwoods, for example, very shallow rooting, cannot handle soil compaction impacts at all, which is weird. But not to be unexpected when you start looking at the growth form, the physiological shape that coastal redwoods take, shallow rooting plants. So we talk about the specific class or type of resources and just kind of go through what the base assumption is for that whole class of resources in terms of how it interacts with human recreationists. We don't care about tree physiology on its own for this class. We care a lot about how tree physiology responds to having someone's initials carved in, or low-hanging branches ripped off of a live tree for ignorant fire building, stuff like that, okay? In the second module under each of these, we'll get into the impacts and the specific ways in which behavioral presence and actions and consequences of those actions affect that type of resource in common or characteristic patterns that we see all across the globe. So, people have been carving things in trees forever. For example, back before the United States was the United States, and just after Spanish incursion into Central America and the southeastern, what would become the United States, we have shepherds, sheep herders moving Spanish flocks of sheep through what is now the American Southwest, places like southern Colorado, Arizona, New Mexico, and it's pretty lonely work, and so there are still a few examples of trees that have been graffitied by Spanish shepherds 3,500 years ago of like figures of naked women, because, you know, there's not much else to, I guess, look at out there, and that was how they passed the time. So that kind of thing has an effect on the tree. And the tree, most likely, in the case of all of the surviving examples 3,500 years later, the tree was resilient enough from that impact of having something carved in its skin to continue on, heal over that wound with fibroids, or essentially scar tissue, and now we can talk about it in class in 2023. So, we talk about the resource, its characteristic patterns, its needs, its limits, in terms of stuff like resistance to impact, the ability to shrug off impact in the first place, and resilience from impact, the ability to bounce back or regrow or regenerate or stump sprout or whatever that physiological response might be. So, resource, impacts, resistance and resilience, moderating factors, things like, what about a tree that's at really high elevation or really low elevation? Or what about evergreen versus deciduous? Or any of the other factors that don't necessarily steer the interaction, but might make it more or less survivable for this resource, if it's a biotic resource like a tree, or an abiotic resource like bedrock. Bedrock, highly resistant to impact. Bedrock, zero resilience from impact. It will never regrow something that we've carved into the rock. Okay? So, talk about the resistance and the resilience, the moderating factors, and then finally, we get into what are some of the management practices of foresters and park rangers in specific relative to that specific class of resource. So, how do we manage, in the case of something we'll talk about a little bit more today, speleothems, stalactites growing down from the top of a cave, stalagmites growing up from the bottom of a cave, soda straws, flowstone formations like Niagara at Mammoth Cave and stuff like that. How do the rangers put a trail through there based on the specific characteristics and needs of this abiotic resource and so forth? Okay, so we're looking at 4 or 5 different sort of classifications or areas of information underneath each of these probably 8 or more classes of resource, and that's going to again take us through about the first half of our semester. The back half of the semester is going to be much more now that we know all of those, across all of those, let's start applying those to your particular chosen park for this semester. So as we go through each one of these different classes of resources beyond terrain, topography, topology, and geography, which you've had a chance to start looking up for your particular chosen park this semester, we want to crack open the National Park Service website for your park, nps.gov/ whatever 4-letter code is for the park that you've chosen off of that website. MACA for Mammoth Cave, ACAD for Acadia National Park, POGO for Potomac Gorge or C&O Canal National Historic Site, as it's also called, and so on and so forth. Rocky Mountain National Park, ROMO. So you want to crack open the nps.gov website and take a look for whichever class of resource that we're talking about. Does my chosen place this semester, does it have bedrock? Yes. Okay. Does it have caves? Yes or no? It may or may not. A place like Ozark National Scenic Riverways, the bedrock is half the fun. The flowing part is just kind of cool and right in everybody's face, but really there's a lot more going on at Ozark National Scenic Riverways than the riverways. So the bedrock is where the action is on that one. So head to the nps.gov website, and just for that one class of resource, there's a ton of information on all of these. Right? This is all public information as provided by the federal government. It is not in copyright and so forth. Right? It is there for your consumption. Your tax dollars have generated those facts. We might as well use them. So pull up on the website and take a look at what's going on with the bedrock resource. And start to learn the character of the resource. So is your park primarily on top of granite bedrock? So we're talking about granitic geology. This is, in the case of granites and basalts, magma that has cooled under the surface of the earth. It was never up at the surface. And the overlying rock, the overburden, has worn away and left some really cool, like frozen ripples in the magma that we call mountains. Pretty cool stuff, okay? Is it karst or limestone geology, which is completely different than granitic geology? In the granitic underlain northeastern United States, like northern New England, Maine, New Hampshire, Vermont, we have really thin granitic, very acidic soils. This is why cranberry farms are where they are. It is perched watersheds trapped on top of granite, which has zero cation contribution to the water, the bog water. And so, in some cases, the bedrock leads to ponds in places like Acadia National Park or White Mountains National Forest up in the Northeast that are more acidic than vomit, lower than pH 4. Low enough pH to preserve human bodies brained and shoved into those bogs, where we get bog mummies from in places like Ireland, Scotland. Okay? So, we want to know, for your park, wherever it is, what is the geology? At Haleakala National Park, nps.gov/ H-A-L-E. The underlying geology is volcanic cinder. And so they have caves, but they're not karst limestone caves. They're not wet caves like we're used to. They're lava tubes that sometimes run for miles down these slopes and serve as burial chambers for native Hawaiian royalty. Completely different than Ozark National Scenic Riverways. So, as a park ranger, we gotta know a little bit about geology. And we gotta understand the interface of humans from the recreation side and from sort of the cultural presence side of native Hawaiians wanting to bury their royalty in the bedrock resource of what is later designated a national park. Some of those remains are many, many centuries old, and, mainland United States comes in, helps with the deposition of Queen Liliuokalani, and now we are managing grave sites in Ozark National Scenic Riverways from largely Caucasian, Western European settlers, and we're managing grave sites for native Hawaiians that migrated in the Great Pacific Diaspora. We're park rangers. What do we know about graves and lava tubes and stuff? But we need to know a little bit about graves and lava tubes and so forth. How do people want to use what is present at each of these places? Before it's a park, native Hawaiians. After it's a park, backpackers and naked hippies. Another story for another time. Okay? So, for each of these, as we get into these different units, having done terrain topography topology already, and now into bedrock and soils, a little bit out of order, a little bit disjointed because I missed last Wednesday. Crack open the website, jump on scholar.google.com while you're on the campus network, and you can download all kinds of academic articles about these things for free. Okay? So, you're not on the hook for any other park than the one that you've chosen. And if you decide to change your mind and pick a different park, you want to do that early in the semester so you don't have to go back and pick up this stuff and a whole bunch of other units after having already done it for one place and now wanting to switch. Cool? All right. Big long sermon for pull open your browser at some point and look up each of these kinds of resources. One of the 4 or 5 different sort of specific commissioning legislation missions of the United States National Park Service is to conduct science. So if these parks, the parks that you are getting to know this semester, or your one chosen park this semester, if these are the places that the United States, one of the wealthiest, most powerful and influential nation states of all time, if this is the class of land that we are calling preserved land, and we're going to hold it to the absolute highest management standard out of all of the different kinds of land that we have in the United States, all of our hundreds of millions of acres, then the science that we can do using these places and these resources within each place as a benchmark, a ruler or a meter stick or a yardstick if we want to use freedom units, against which we can compare everything else, well, then these sites are pretty important. So they have been studied to death. So there's a lot of info for you to find about each of these places, or a lot of info available, I should say. We want to understand and be able to explain the bedrock resource, for example, to the level of, at Ozark National Scenic Riverways, it is primarily karst, which is limestone and sandstone here and there, but it forms sinkholes, lots and lots of miles of caves, big springs, and a complex fractured hydrologic regime. There's stuff flowing over and below and looping back around through these cave tunnels and stuff like that. It's total chaos hydrologically. But that's all a function of the bedrock. Because it's limestone and it's easily dissolved by the minor natural acidity of rainwater, the whole place is like chronic wasting disease brains. It's just spongiform. There's lots of pockets and channels and cave galleries and rooms and sinkholes where it interfaces with the surface, and so on and so forth at Ozark National Scenic Riverways. The level of detail that we don't need for this class is stuff like, well, in the soil section, we don't need to know that it is pre-Aeolian Alfred silt loam and Peoria loess over that karst limestone bedrock, right? We just need to know that, okay, this is limestony soil out of a limestone parent material, and so we're going to get very specific vegetation ecosystems that we need to know about and protect as park rangers at Ozark National Scenic Riverways, like limestone glades, which are these beautiful and not super common anymore, but beautiful, 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 and unique and fragile ecological communities in places like Ozark National Scenic Riverways, okay? So we don't need it down to the soil order and series. We don't need to know the mineral cleavage patterns, like the crystalline structures and shapes of each particle of the mineral of the bedrock and so forth. But in more general terms, is it hard bedrock? Is it soft bedrock? Is it easily erodible or carved into? Is it unusual, or is it ratchet, basic, common? Okay? Look at that level. So we don't need to be geology majors and wildlife majors, zoology majors, and all of the other things, but we just want to have some clear functional sense of what am I basically looking at from 40,000 feet as I'm flying in to be a park ranger there. What can I see at that distance? Okay? Cool. So any questions on the basic structure and outline of each of these different things? We're going to spend the next several weeks on moving through these, so I just want to kind of get the blueprint out there, the template. It's cool. All right. Resource, impact patterns, moderating factors, resistance and resilience, stuff like that, and how do we manage it specifically with respect to forest and outdoor recreation. So I'll put some of those materials on for bedrock and soils onto our course website. 4. Let's see here. For these, we want to get a couple of general concepts in place. We mentioned resistance and resilience. Let's go through those a little bit more. Do we have any either Dungeon Crawl Classics or 5th edition folks, Dungeons and Dragons players? All right. Any gamers more broadly? Okay. So, we can think of resistance as the resource, whatever it is, abiotic like bedrock, partially living like soil, whatever. Resistance is like its armor value. Okay? It doesn't matter how hard you punch someone in steel or ceramic plate. If they're wearing like a bulletproof vest, it doesn't matter how hard you punch them, you're not going to fists of fury your way through their body armor, okay? So resistance is the ability to ignore or prevent impact in the first place. And impact, again, is just any kind of change, positive or negative. We're generally talking about negative impacts when we're talking about resource impacts. But we do sometimes, rarely, get a positive impact in typically an animal population in specific places in specific ways. So resistance is like armor. Resilience is the ability for that creature or that resource or what have you to essentially regenerate the damage away to the point that it is functionally completely gone. So we can have sort of a complex blend of these two things in any particular organism. Or it can be fairly straightforward. So, again, a mature tree, a 150-year-old oak tree, you're probably not going to step on it to death. Very high resistance to trampling impact, even walking impact. A 150-year-old healthy oak tree, assuming it doesn't have any insect pathogen problems or like an oak rust or something like that, so a fungal infection or a viral infection, also probably has very high resilience. For example, if we did saw off one of those limbs because we're idiots and we're using a pole saw on our campsite to fell a live green uncured limb to throw on our fire and just sort of look sadly at it as the moist hardwood fails to catch for hours and hours and hours because we are ignorant, it's probably not going to kill the tree. Because of what, foresters? What kinds of biological resources does that tree have to hand, already stored up, so to speak, in order to heal over that amputation? How does an oak tree survive having a limb cut off? A perfectly healthy limb.
So the sap come out, like, just kind of cover the surface?
Right, eventually. So, acutely, we're going to have a bunch of sap leakage, depending on if we are early or late in the season, if the sap is going up or down, root to shoot or otherwise. And slowly that's going to eventually, in most cases, heal over, right? The living layer of the tree inside the outer bark and outside of the heartwood sort of bubbles and grows over that amputation site, and we all know exactly what that looks like. We've seen good and bad examples of tree trimming and so forth. So, that's not a question of preventing the damage. The damage is a saw chopping through the limb. It's not automatically an existential problem for that tree, but it does cost that tree some of its finite resources in terms of sugar and proteins storage to regenerate that site to essentially stop the bleeding over the next couple of seasons and move on through, okay? So, for biotic resources, this is a pretty dynamic thing. If we hit that oak tree with the exact same behavior, chopping off the same limb of some identical theoretical clone of our first tree, if we hit that during a drought, the tree is going to have less resilience, but about the same resistance in the first place. Okay? There's less water, so there's less sap and carbohydrate, protein storage, and so forth. So it has less biomass, if you want to think of it that way, to regenerate that damage. Okay? And then in other years, maybe in a more well-fertilized environment, maybe the tree is just already growing gangbusters and chopping off even a major limb doesn't really slow it down that much. It's already got a surfeit or an unusable surplus of resources like soil ions in the form of different fertilizing chemical species, nitrates, phosphorus, carbon, and so forth. Okay? So, resistance, armor. Resilience, healing spell. Cool. Now, this can get overwhelmed. So if we keep cutting off limbs, well then eventually there's just too much blood loss or not enough resource already uptaken, and stored in the root mass ready to go to bounce back from that, and the organism, in this case of a living resource, starts to die back. And that dieback might be a decades-long process, or it might be basically instant. So, resistance and resilience for not a mature 150-year-old oak tree, but for A wild blue. Does anybody like blueberries? I love me some blueberries. My wife and I fell in love at Acadia National Park, which is covered in blueberries, just like nature's neckbeard. They're everywhere. It's awesome. And so blueberries are important to me. Unfortunately, low bush or wild blueberry, high bush, the cultivar blueberry trees grow 6-7 feet tall. You get the big fat blueberries, which are mostly sugar and no flavor. The wild blueberries are mostly flavor and not a ton of sugar, so they can be kind of tart. It's really awesome. They're real small. Low bush blueberries put out lots of blueberries kind of late in the summer up in northern New England at places like Acadia National Park. And they're delicious. And there's a billion of them, and they all sort of pop at once on these Atlantic seaside dwarf blueberry shrubland complexes that they are in. Unfortunately, when they are popping, overlaps. So the berries are fruiting out. That time period overlaps kind of like July, August into September, maybe just July and August, with the peak season at places like Acadia National Park. So you have anywhere from 2 to 4 million visitors a year on a fairly small horseshoe-shaped island called Mount Desert Island, which is the heart and soul of Acadia National Park. There are other units elsewhere, but this is the one that gets millions of visitors a year. And they're all there after Memorial Day and really before Labor Day, because this is an island on the coast of Maine, and it's cold and wet and rainy all spring long, and it's cold and wet and rainy and then snowy all autumn long. So you got about 3 tight months to fit 2 to 4 million people on this 44,000 acre island. That's a lot of people in a little bit of space. And it's a lot of people in a little bit of space, and some of that space is teeming with wild blueberries. So the problem becomes, for the low bush or wild blueberry plant, it's a woody shrub, it doesn't have the size of a mature 150-year-old oak tree. A low bush blueberry is exactly what it sounds like. It might be between ankle and about mid-thigh high for a pretty big one. And that's just low enough for anything about knee-high or lower on an average, in the United States, 5'10" is about average height person. Anything about knee-high or lower is definitely low enough to Paul Bunyan or big step over or into. So in your mind's eye, imagine what it sounds like as I'm stepping into a low blueberry patch to try and get some that are just outside of arm's reach at the side of a little hiking trail that might get 15,000 visitors a day. Very, very busy trails. Right? What does that sound like as I step down into that low bush blueberry?
A lot of branches breaking.
A lot of twigs snapping. A lot of branches breaking. That's not one amputation, it's dozens of them. Okay? And that low bush blueberry is growing on, it might only be 2 inches of what looks like really coarse sand, granitic gravel, decomposed granite, which is super acidic. And the high acidity means that all of these soil nutrients are leached out and washed away. Those low bush blueberry plants, they are trying to hang on for dear life already, and then you start stepping on them and breaking like lots of bones all at once. Would be the equivalent metaphor for a human getting stepped on by something our size relative to the size of the low bush blueberry. So the resistance to impact for the low bush blueberry, pretty low. Like it can't handle a single step. That's going to change the growth and trajectory and health of that single organism that's been stepped on permanently. You know, if the plant survives till the next season, and most of them do, it's going to have a big hole in it. And that hole looks like it's about foot-sized. For the next idiot, the next season, the next batch of 2 to 4 million people, and now we got 1, 2 steps in. Okay? So this is how this tends to go with natural resources in a recreation context as a function of the plant's just physical size, the plant's hardness or durability. So we're going to use durability in a very specific sense of what is its durometry. How hard is it? How resistant is it to puncturing impacts? Durometry is a measure of puncture resistance. Durable is the positive expression of that trait. Okay? Squishy. For those of you who play MOBAs, squishy characters are low durability. All right. So, it can't handle being stepped on. It's fairly poor site index in terms of soil quality, for those of you who've taken soil so far. So, not a lot of nutrients available. The water that is almost continuously rained down on these low bush blueberries is not staying around. It's going through that sandy soil, which doesn't retain moisture very well at all, and washing out back to the Atlantic. Okay? So, the biomass available for healing that season, it's not even there because it's poured so much of the generated sugars, the carbohydrates, and the proteins to make all of these hundreds and hundreds of berries per plant. It's put all of its resources into that. There's not much left to get that thing through the winter. Does that make sense? Okay. So this is one survival strategy or adaptation for woody shrubs to seed out prolifically. Here in southern Illinois, do we have any shrubs, maybe non-native invasive shrubs, that seed very prolifically? Like 10 to 50,000 seeds per season per plant that birds like to eat and poop out and spread autumn olive all across of our landscape here, right? Unfortunately, we don't have that same reseeding mechanism and the same growth figure for low bush blueberry. So, Acadia National Park, we can't change either of these. And we especially can't change them because it's a national park. We can't just go out there with like backpack sprayers full of fertilizer and herbicides and clear out everything else and just be like, here, little low bush blueberry, have some synthetic nitrate fertilizers. No, this is a national park. That's not appropriate. It's not going to fly. So, instead, our management technique or adaptation or move or strategy or tactic is going to be to take a look at what's the worst case scenario for this plant? Like what's its resistance and resilience in the most dry season during and after the most intense human use and trampling pressure, right? It might only be 1 out of 1,000 people, 0.1% of the visitors that trample while they're getting blueberries, but that's still enough because one person is enough to trample one of these to death in a single day, a single pass. So, what is the worst case scenario for the survival of not just this one plant, but its community of plants all around it? And let's manage to that. Let's manage our visitors to that, because we can't force these to heal up well after they've been trampled. That's kind of a horse is already out of the barn situation. And figure out, okay, do we need to shut down our trails that go through these patches of blueberries? That's going to help those blueberry bushes kind of survive so that any of them are left for next year. And at the same time, we are also managing the human wildlife species. So the blueberry bushes survive a little bit better because of our management, because they are low resistance and low resilience during that particular time of year in that particular place. What is going to be the effect of us changing the human habitat by closing the trail around these blueberry bushes? How do people respond to that? If one of our key rules for this class is you can give, but you can't take away. So what happens at Acadia National Park in the minds and hearts and mouths and emails of visitors when we take away a trail that we had given to them? Most of the trails at Acadia are over 100 years old. People know these trails really well. And they come back to them year after year. What happens when you, the ranger, close a trail to save the blues? What happens, do you think? Remember, we're talking worst case scenario. So what's the worst that could possibly happen?
They go anyway?
They go anyway. They reopen the trail. So, like, we pay people, like our trail crews. Some of you guys and gals may be working on trail crews over the summers. We paid you to bring like heavy, big rocks and cut down trees and pile those at the trail so that people wouldn't walk on the trail. And then they pull all those off again and reopen the trail? That sounds more like work to me than vacation. Surely people wouldn't do that. Yeah, they would. All right? Yeah, they would. Okay, so people reopen the trail, and they go right back to traveling. What else could go wrong? How else could this go wrong? What's another worst case outcome here, other than the trail being reopened? How else could people respond to that, maybe negatively? How else might you respond if I closed in on your favorite trail and you knew there were a bunch of tasty berries further down that trail? Because you've been going down that trail every summer since you were a kid. This is our family's trail in capital letters. How might you respond to that?
I get mad.
You get pissed off. Yeah, absolutely. I would too. So, last time I was at Acadia, they had closed off some of the trails. And what did I do? I'm a professor. And I know better. I went through the woods along those trails. And it was very nice. And I was very ecologically respectable and respectful. But there was stuff down those trails that I really wanted to see again. So, we did. And that is understandable, but it's not good. Because a ranger's only going to close a trail if they really, really, really have to. Like, we're not in the business of ruining people's vacations, right? Half of the point, half of the entire reason for the existence of the United States National Park Service is to provide amazing, high-quality access to resources and experiences and opportunities. So, shutting anything down, major red flag of something is extremely wrong or this management team is going off half-cocked. Okay, so that is one sort of detailed walkthrough example of what is the resource? Blueberry bush. What is the impact pattern? Broken limbs. What is a moderating factor? Poor soil quality, poor site index. What is a management tactic or response that can be used? Close down the trail, remove access to those, at least temporarily, and see what happens. Okay? So, resistance and resilience. Good? All right, cool. Let's see. 4 bedrock resources. We want to include things like caves, lava tubes, and so on and so forth. So, we tend to think of bedrock resources as extremely resistant to impact because we're not going to run out of bedrock anytime soon, and that is true. Unfortunately, the caves and the lava tubes and the ecosystems that are obligate to those things, like cave crickets, cave species of fish, and so on and so forth, where their early ancestors, like J.R.R. Tolkien in The Hobbit, their fathers swam in, and then their eyes grew big, trying to look for anything in the permanent darkness That's how he describes Gollum's Lake. Pretty cool stuff. The guy was like a recreation ecologist. He didn't even know it. Okay? Those ecosystems that are obligate to underground systems, to lava tubes and so forth, they are extremely hard to find anywhere else, typically. It's a function of the specific latitude that they're at in terms of ambient temperature year-round, stable, 55 degrees at Mammoth Cave, for example, year-round. And the specific species that can get in and stay in, and the weather patterns that continue to bring in nutrients or prey for those species that are obligate to the caves, because they can't swim out, typically at that point. They get washed into some deep pool that doesn't have a connecting or swimmable or navigable exit point. Okay? So, bedrock resources, kind of regardless of whatever type of mineral it is, whether it's a harder granite or a softer sandstone or a very soft talc or chalk material, like the White Cliffs of Dover over in the UK. That is highly resistant to impact, typically extremely low resilience from impact. So anything that anybody does that does change the environment there is going to be there functionally permanently. Has anybody ever been to a cave before? A karst cave, a limestone cave where they have stalactites and stalagmites. Okay, most of us. Good. All right. Have any of you been to, or do you remember in that cave trip, walking by any speleothems, typically stalagmites growing up from the bottom, so those sharp conic shapes? They look like fangs. Have you ever seen one of those sort of flat-topped and capped off by, it's typically sort of a tan or yellow color, looks like icing almost on top? Okay, do you know what that is? That is the oils and the sunblock and the bug spray and the moisturizer on your hand completely altering the extremely delicate balance of dissolved and precipitated, that is, in solution and out of solution limestone mineral. You put a little bit of oil on top of that, and you're stopping the growth or formation of that growing cave feature for tens of thousands of years in most cases, except in the most wet cave environments where you're eventually going to wash that oil off by just splattering it with drops over and over and over the course of several thousand years, right? So just the act of touching something in a cave ecosystem is enough to stop that feature from changing and growing and alter the chemical environment, sometimes irretrievably. In places like southern Missouri, central Kentucky, where we have Mammoth Cave in Kentucky and all sorts of cave systems in southern Missouri, in the northern Ozarks. Sometimes the impact to the cave or the bedrock resource is exogenous. Our next term is going to be exogenous versus endogenous. Exo, from the outside. Endo, from the inside. Gen, living or started. So, something that is started from the outside, exogenous. Sometimes those impacts are exogenous. At Carlsbad Caverns, which is not a limestone cave system, I believe it's it's something else, I think. At Carlsbad Caverns, which is a very large cavern complex out in the southwest, the United States National Park Service received the mandate to manage Carlsbad Caverns as a nationally and internationally significant cave system, and it is. It's amazing. And so they put in a visitor center, they got roads paved to the area, put in some parking lots, and what do we normally get out of parking lots other than cars and out-of-shape people? Anybody know what flows off of parking lots like every time it rains? Oil, crankcase fluid, antifreeze, all kinds of different chemicals. In a typical automobile, there might be as many as 200 to 300 additives in the gasoline alone. And every once in a while, some of those chemicals drip from the bottom of the vehicle onto that parking lot surface. And every once in a while, in the semi-arid Southwest, we get some rain, and that liberates that lightweight, immiscible in water oil into the cave system. So the National Park Service, it was found, was actually responsible for creating some pretty heinous petrochemical contamination of a completely unique cave system. We can't go to Walmart and buy another Carlsbad Caverns. We can't replace it. We can't fix this either. It's just a thing now, right? It's a one-way impact because there's no resilience for flushing chemicals out of a cave system where it's a semi-arid environment in the first place. There's not that much water. There's just enough to get those chemicals in there kind of forever. Okay, and some of them are forever chemicals. So, in that case, the Park Service had to do a whole bunch of science and research to figure out, okay, we can't just shut down Carlsbad Caverns. We can't take that away from people. We can't fix it, so we got to do something. And what we can do for this bedrock resource, in terms of the fourth stage, right, the resource, the impact, the moderating factor, and then the management of it. In the management phase, the source of the problem is these parking lots. So let's move the parking lots out of the upper watershed of the cave system, right? So physically above it, move it somewhere else. And let's put in a new parking lot wherever we put it in a way that captures any overland flow perfectly. We can't have any leaks from our parking lots. Let's put a state-of-the-art, like, amazing S-rank, for those of you gamers out there, water treatment facility, primary, secondary, and tertiary in particular, water treatment facility to remove all of those petrochemicals, all of the plastic dust blowing across the landscape, all that stuff. None of that will be in the water that we discharge into the cave system. That sounds really expensive. And to the visitor, it's like, oh, well, last time I was here, there was a parking lot there. Now it's over here. I guess we'll just park over here, right? So sometimes your management as a park ranger, your efforts are going to go completely unnoticed. And sometimes that's a good thing, because maybe the Park Service isn't the point of Carlsbad Caverns. We don't want people focused on the Park Service. We want them focused on, the resource, Carlsbad, the bedrock going on, the rock formations, and the amazing experiences you can have at Carlsbad with night sky and resource interpretation and encountering rangers and all the things you can do at Carlsbad that make it amazing. So, I want to think about resistance and resilience, and be aware that sometimes the threat is from outside the system. It might even be from outside the border of your park. Okay? So for your park, relative to its terrain and topography, and what that terrain, topography, topology, in case like road networks and parking lots, part of the topology, what are those larger scale things bringing into your park? The exogenous threats. And then once people are in the cave system, are they touching in a karst cave system, not Carlsbad, but in a karst cave system like Mammoth Cave, where speleothems are actively growing out of the ceiling and growing up from the floor and sometimes connecting into columns? We have some endogenous threats. People touching those even once can screw them up for thousands of years. People knocking them over so they can take a piece of that home and stick it on their mantle above their fireplace is another kind of endogenous threat, and a very common one at places like Mammoth Cave, where there are a gazillion speleothems to look really cool and just be like, oh, I knocked into it. Oh, well, the park ranger's way up there. Let me throw this in my backpack, right? So we have exogenous threats or impacts, negative impacts, and endogenous threats and or impacts for all of our different types of resources. And for bedrock resources, that's going to be things like cave impacts. Okay? Cool. We're right about the halfway mark, so let's take a quick, about a 5-minute break here. Stretch your legs a little bit. And if you'd like, let's kind of reconvene outside. I don't think it's too hot out. Would it be okay in the shade? All right, let's do that. So we'll reconvene at the top of the hour here and then head outside. We'll dismiss from the field today. Stretch your legs, use the restroom if you need to.
Still able to do that map geolocation assignment? Okay. I'll just set that up.
All right, as a quick tag on for where we are heading on the back half of the semester, just in the corner of the chalkboard here, I've got 4 organizing broad strategies, and you've seen these before if you took Rec Summer Camp this past summer. These are how we're going to sort of categorize our plan responses or ways to avoid, mitigate, repair impacts to all of these different types of resources throughout. So first, we're going to increase the supply of the resource in real or effective terms. We'll talk about what that means later on. We'll improve the resource itself. If for some types of resources, there's a way to make it physically more durable, or to modify a migration corridor a little bit to move it away from some injurious human encounters and so forth, we can improve the quality of the resource with some, typically it's going to be something like light and easy and elegant, or it's going to be this huge billion-dollar snafu, okay? Third, we can modify human use in time, in space, in character, in type. There's a lot of things, a lot of knobs we can twist on that in terms of like issuing permits differently, or having this trail open Monday, Wednesday, Friday, but not Tuesday, Thursday for some reason, or something like that, okay? Lots of ways we can modify human use. And finally, our fourth and least desirable strategy, it is always our strategy of last resort, is to limit use. If we have to, we can cut off the bleeding and stop people from using a resource at a particular time or in a particular way or what have you, okay? That is never popular, even if it's the right thing to do. So it's always our method of last resort. But we'll talk more about this kind of come mid-October or so. In the meantime, we'll get through all of these resources and talk at times about what are some different tactics or strategies that we can sort of use with each type of resource or in specific situations.